The Big Defreeze theory briefly suggests that at the beginning of the universe, all matter started with a single collective quantum wave, which could be referred to as the identity stem wave of the universe, ISWU. In other words, the universe was in a frozen state at almost absolute zero temperature and potentially shrunk in a very tiny collective wave, the identity stem wave of the universe, ISWU. This stem wave started gaining energy, leading to fluctuations behaving in the manner of a string, forming what could be referred to as the identity stem waves of matter, leading to a supersymmetrical crystal. Of course, colliding all the matter that we know of, or at least one of each matter to shatter them to their elementary particles, and then cooling the shattered particles to degrees close to absolute zero to see if they will form Bose-Einstein condensates would be quite challenging, to say the least, and if we manage to do so, we will potentially be creating a new Big Bang. However, this sort of what is going to happen with the Big Rip scenario, where all the matter that we know of will be ripped. Then the next step, as proposed here, would be the heat death of the universe. So basically, the Big Freeze scenario would be modified a bit. It will basically be a scenario following the Big Rip, where, after all matter is shattered, ripped, the universe will head towards the Big Freeze, and the shattered particles will form Bose-Einstein condensates, leading to a collective quantum wave, which is proposed to be similar to the collective quantum wave, referred to in this book as the ISWU, or the identity stem wave of the universe, at the beginning of the universe before inflation. For bosons and ideal gases, we know how to do experiments on them to form Bose-Einstein condensates. The challenge would be for the matter, which is neither bosons nor ideal gases. We will potentially need to do a fermion to boson transformation as suggested in the fermions problem earlier in this book. The cold atom lab could be a very good candidate to carry out such experiments. Again, it's quite challenging, but in principle, if we manage to break down matter to its elementary particles in the cold atom lab, and then cool them down to near absolute zero and see what happens, we can start understanding the behavior of the ISWs. We can also introduce 2 different types of matter, then 3 different types of matter, and so on. Something to consider here, though, should we see how many elementary particles these matters are composed of, and try to sort of isolate this specific number and configuration of elementary particles and introduce it in the cold atom lab? Or do we need to do the actual colliding and shattering of particles? This is something that needs to be tested. The first method could yield good results. However, it is expected that the results will not be the same as if you actually collide and shatter the actual matter that you want to test. And this will not be because of some spooky action of knowing the history of the tested matter. It would be simply because of the idea of the evolution of information wave function of this matter, which is expected to have an impact on the result, even if we use the exact same number and configuration of the elementary particles of this matter. Another point that is worth considering is the interaction with the environment. Even if you carry out the experiment in a vacuum, you still have the radiation of the cosmic microwave background. There is always some environment. Yet, let's consider the proposed identity stem wave supersymmetrical crystal at the beginning of the universe. It was only interacting with its constituents, which are expected to be the newly born identity stem waves only. That was a very pure environment, and that was the only environment without any other interactions or cosmic microwave radiation. This means that potentially we can create identity stem waves and study their behavior. However, in a sense, we cannot create the same environment as the one of the proposed identity stem wave crystal at the beginning of the universe before symmetry breaking and inflation. The idea of the big defreeze of the universe suggests that the first identity stem wave that started fluctuating is that of iron ISW Phi with a frequency of approximately 510 to the power of -5. Then other ISWs started fluctuating until the ISW of helium ISW, He broke the symmetry of the ISW crystal with a value comparable to the speed of light. In the 1990s, more precise measurements found that the cosmic microwave background, CMB, is not perfectly smooth, but it has ripples in it. Inflation theorized that these ripples are the result of quantum fluctuations that were amplified when the universe expanded. The temperature fluctuations dTT equals sine 10 to the power of -5. These tiny fluctuations can be mapped. When you look at the structure of these fluctuations, you can Fourier decompose them, and then calculate the power spectrum of these fluctuations. You find that you can get evidence from how these tiny fluctuations form. That, for instance, most of the gravitating matter in the universe is actually invisible. It is dark matter, we only see it via its rotational effects, among others, on how these fluctuations were formed. It is also the stuff that keeps the galaxies together. If we do not have this dark matter, they will just fly apart, and they will rotate too fast. And we also have evidence of dark energy, which basically behaves like the cosmological constant, which has been now measured. It speeds up the expansion of the universe. It accelerates it. If you take these tiny fluctuations, they cause variations in temperature and also in the density of matter, and therefore variations to the gravitational potential. You put it in a computer, run it forward, you find that these tiny fluctuations generate all the large-scale structures of the galaxy clusters and superclusters that we see today in our universe. You can show that wherever you find deviations from the mean temperature, you find clusters or voids. You can map this. When you Fourier decompose it and compute the power spectrum of the two-point function of these fluctuations, you see that there are distinct structures in there. There are waves, sound waves basically, that propagated through the hot plasma before it cooled enough that hydrogen could form. When you analyze the properties of these fluctuations, you see that besides all the local dynamics like sound waves, the way how the sound waves interact with the plasma, the way how the plasma interacts with the photons, etc. Overall, you find a very remarkable structure. You find that the waves that cause these tiny fluctuations in the temperature were generated with having the same power on all wavelengths. So they have what is referred to as the scale invariant power spectrum. And they always come with an initial coherent phase condition as if they are coming from a broadband laser. This is considered evidence that there was a very early phase, much earlier than these 400,000 years after the Big Bang on the CMB, of the expansion of the universe that was much faster, exponentially fast, and this called inflation. The big Defreeze introduced in this book predicts that the source of this coherent scale invariant fluctuation is the identity stem wave of iron ISW Phi. So, when the symmetry was broken by the identity stem wave of helium ISW He, as predicted in this book as well, the ISW of iron maintained its power on all wavelengths as it did during the ISW crystal phase in maintaining its power on all the other ISWs, leading to the interactions in the ISW crystal. It is like the ISW of iron acts as the source of the laser beam in the CMB, and it maintained its power and properties, including coherence and scale invariance. What was the source of the initial fluctuation in the ISW of iron? Please refer to the straight-line analogy and the proposed imaginary complex forces introduced in this book. This would be evidence for the big Defreeze if we managed to shatter iron to its elementary particles and carry out a fermion to boson transformation, then cool them down to near absolute zero to notice if a BEC would form. Then, if we found that the Tc to form this BC is comparable to 510 to the power of -5, then we have experimental evidence for the big Defreeze. Despite the experimental challenges of actually shattering iron to its elementary particles, it is expected that it would yield more accurate results to do it, rather than considering how many elementary particles iron has, and cool them down. And as explained earlier, This will not be because of some spooky action of knowing the history of the tested matter. It would be simply because of the idea of the evolution of information wave function of this matter, which is expected to have an impact on the result, even if we use the exact same number and configuration of the elementary particles of this matter. As it is clear, the idea of the Big Freeze is totally compatible with inflation and the Big Bang, with a tiny difference, which is that the very first phase of the universe, which was tiny and condensed, was not hot, it was cold. And then it got heated to a very high temperature through the symmetry-breaking mechanism of helium's ISW. The era following the symmetry breaking by the ISW of helium leading to the bank is predicted to have the following operations. The transformation from 2 dimensions to 3 dimensions could be tracked using Riemann curvature and Ricci scalar, as explained earlier in this book. The identity stem waves of all matter ISWs were sort of freed and accelerating with speed comparable to the speed of light. Interactions happened between waves, and waves started gaining mass through the Higgs field. The ISWs started gaining more energy/heat. The acceleration is leading to an exponential increase in energy/heat and exponential expansion. The proposed imaginary mother forces will start acting on these waves with their operations, including creation and annihilation, resonance, scaling, and projection, with a note that these forces existed before the ISW crystal was formed. How can we observe and track this in the cosmic microwave background? The answer would potentially be the tiny fluctuations in the cosmic microwave background, operations of the imaginary complex forces, evolution of information. The Big Defreeze predicts that the tiny fluctuations in the cosmic microwave background could potentially be the only fluctuation that maintained its full identity, coherence, behavior, properties, including scale invariance during the first 370,000 years of the universe and till date. These fluctuations correspond to the identity stem wave of iron ISWFE in the Big Defreeze. That does not mean that the other ISWs lost their properties. Basically, they are proposed to be identity stem waves, which means they preserve, at least partially, their identities and properties. What it means is that the ISW of iron, or the tiny fluctuations, is predicted to be the only ISW that has fully maintained all its properties and power, and that is what we can currently observe on the tiny fluctuations in terms of having the same power on all wavelengths. This prediction could potentially give us a great tool in tracking these fluctuations and their behavior and interactions during the 370,000 years, as it would be the only wave function that behaved exactly the same. The techniques used for the experiments to detect the BCs, interference of 2 BCs, and transferring them, especially the ones developed by Wolfgang Ketterle and his colleagues, could be very useful in testing the idea of the identity stem waves and their interactions. Since the ISWs are basically a type of BC, we expect to detect them and study their behavior and interactions mainly using the same techniques used for experiments on the BCs. We can do that now for bosons and ideal gas, which would potentially be sufficient to detect how far these predictions are correct. The main challenge would be for non-bosonic matter shattered into their elementary particles and transforming fermions to a bosonic quantum behavior like the Bose-Einstein condensation. We have proposed potential solutions for that in the fermions problem section in this book. Another challenge would be the actual shattering of matter to maintain its history of information. Laser cooling. The principles of laser cooling are pretty simple. You shine laser light on atoms, the atoms scatter light, and if you play some tricks, the light that is scattered emitted has a shorter wavelength and is more energetic than the absorbed light. The scattering of light removes energy from the system and the system cools down. Magnetic traps. There are 2 types of magnetic traps. Some have a pointy potential, a linear V-shaped potential, and others have a round potential at the bottom. Those traps are more tightly confining. Interference pattern experiments. Let's go back to the interference experiment by Ketterl and his colleagues where you build two condensates, so you basically have lots of atoms in the ground states in each of the two traps, and then you turn off the traps, let them go. Then you can measure the distribution of atoms as a function of position. They basically saw fringes in the atomic density because the two condensates were interfering with one another. The same experiments could be applied to the predicted ISWs. We can do that easily with bosons and ideal gas. The optical trap could be used as a transport mechanism for the identity stem waves as well.